Hi everyone, this is the video lecture for class 18 of PH 125, and today we're going to be continuing to talk about potential energy. Specifically, today we're going to look at potential energy curves, and then we're going to continue thinking about conservation of energy, and we're going to talk specifically about non-conservative work. Okay, so just a quick reminder, last time we talked about two different types of forces, conservative versus non-conservative forces. And remember, conservative forces that do work that is path independent, right? So that was that idea that if you took any path, the work done between the final and initial states would be the same. Okay, and so then what we learned is that the work done by a conservative force is equal to minus a change in potential energy that's associated with that force. And so we talked specifically about two different types of conservative forces, gravitational force and the restoring force or the spring force. And so then we have two associated potential energies. So we can talk about the potential energy due to gravity, which is mgy, or the potential energy due to that restoring force, the spring force, which is 1/2 kx squared. Okay, and so then if you have either the spring force acting or gravity acting, it will do work on the system that causes a negative change in that potential energy. All right, and so then in contrast, we have non-conservative forces. So the classic example of a non-conservative force is friction. Non-conservative forces, when they do work, it is path dependent. So it depends on the path taken between the final and initial states. Okay, and so then we characterize that work, we call it WNC, whereas the work done by a conservative forces, I'll call it WC a lot, or W conservative. Okay. All right, and then remember before that we talked about another type of energy. In addition to potential energy, we talked about kinetic energy, right? And so K is equal to 1/2 mv squared. And then last time at the very end, we defined mechanical energy, which is the sum of all of the kinetic and potential energies of the system. So this could be the potential energy due to gravity, the potential energy due to the spring, if there's a spring present, or both. Okay, so it's the total kinetic plus potential. All right, and so then what we learned is if only conservative work is done on the system, so in other words, there are no non-conservative forces acting. So this would be any situation where you're told the surface is frictionless or something like that. Then you know that there's only conservative forces acting on your system. And then what we know is that the total work is the same thing as the work done by conservative forces, since there are no non-conservative forces acting. And so then it turns out that we can talk about conservation of mechanical energy in this case. And so then the change in mechanical energy will be 0 as long as no non-conservative forces are acting on the system. So in other words, you can compare initial and final states of the system, and they will have the same total mechanical energy, in other words, the same kinetic plus potential energies. Okay, so let's do a quick little example to get started today. We have a massive ball M that's dropped from rest from a height h, and it lands with speed v. Okay, and then we want to think about what happens if we drop a second ball. This ball has mass 4m, and it's dropped from rest from a height of h divided by 4. We want to know what is its speed. Okay, so let's see how I would go about solving this problem. This is one of those problems where you're going to want to set up a few cases. So let's start with case 1. Okay, so in case 1, we're told that the ball has mass m and it's dropped from rest from height h and it lands with speed v. Okay, so we want to set up initial and final states for both of the two cases, and then we'll set the energy in the initial and final states equal to each other. So let's start with E initial. That's going to be the sum of K initial plus U initial. Here we know that K initial is 0 because it's dropped from rest, right? So this guy's actually going to be 0 since V initial is 0. And U initial is going to be mgh. Okay, and so here E initial is going to be equal to mgh. All right, now let's talk about E final. Just before it lands, so that means when the height h is equal to 0. So we're going to have K final plus U final, where U final is now going to be 0 because we're at a height of 0. Okay, and so then what we're left with here is 1/2 mv squared. All right, and so then because we have E initial is equal to E final, we know that mgh is going to be equal to 1/2 mv squared. All right, so let's keep that in mind and look at our second case here. Okay, so now we have E initial, which again is the sum of kinetic and potential energies. It's dropped from rest, and so we're still going to have K initial equal to 0. All right, plus U initial. And now U is in general mgh. So here our mass for case 2, it would be m2 g2 h2, which is really the mass of case 2 is 4m. G is the same. I shouldn't have put a 2 on that, sorry. And then H in case 2 is really H divided by 4. Okay, so that tells us that our 4's should cancel here, right? So we have 4m and H divided by 4, and so I really just get mgh for my E initial. All right, now we need E final. All right, and so E final, once again, it's at this landing height, so that's where H is equal to 0. And so now we're going to have K final plus U final, where U final is equal to 0. And here there are no springs, so I'm just talking about potential energy due to gravity. All right, and so then K final is equal to 1/2 m2 v2 squared. Remember, m2 is 4m. Okay. And then we have V2 squared, and that's the thing we're looking for. We want to find V2. All right, and so now what I can do is I can set my initial and final energies equal to each other for the second case. So remember, E initial was just mgh is equal to my E final, which is 1/2, let's pull that 4 out. So 4 times 1/2 mv2 squared. And so then I can look at my case 1 over here. For case 1, I found that mgh was 1/2 mv squared. And so what I can do is I'm just going to plug that in for mgh over here in case 2. So that tells me that 1/2 mv squared is equal to 4 times 1/2 mv2 squared. Okay, my 1/2s cancel, my m's cancel, and we're left with v squared is equal to 4 times v2 squared. And so then v2 is equal to the square root of v squared divided by 4, which is really just going to be 1/2 of v. So I would say that the answer here is D, 1/2 of v. All right. So now we're going to think about potential energy curves. And so remember, potential energy is always related to the way objects are positioned in a system, right? So for potential energy due to gravity, that's height, so the height in the y direction. And for springs, it's going to depend on that stretch from equilibrium. Okay, and so in either case, it's dependent on position. And so it turns out that it can be very useful to think about potential energy curves as a function of position. So let's start with potential energy due to gravity. If we have an object that's moving along some path in both the x and y directions, and it's under the influence of gravity alone. So really there's actually going to be a normal force acting as well. But when I say gravity alone, I mean that there's no friction. Okay, so no friction means that we have no non-conservative work being done on the object. Okay, so then we remember that the potential energy due to gravity is really equal to mgy. And so what we can do is think about the fact that the potential energy due to gravity is proportional to y. And this is important because then this tells us that a plot of potential energy versus x is going to look exactly the same. It's going to have the same shape as a plot of the y position versus the x position. And that's just because gravitational potential energy and y position are proportional to each other. So let's look at an example here. In the top plot, I have a track, and I have a ball that's on this track. And so then it turns out because the potential energy due to gravity is proportional to the height in the y direction of the track, then that tells me that the potential energy of the ball at any position along the track is really just going to be proportional to the height of that track. And so if you look at the bottom curve, which is a plot of the potential energy due to gravity versus x, it looks exactly the same as the path taken by the ball, or in other words, the plot of y position versus x position. Okay, and this can be really useful for a few reasons. So first of all, we know that the total mechanical energy, because I don't have any friction acting, the total mechanical energy is going to be some constant value. So in other words, the potential energy due to gravity plus the kinetic energy is going to be constant. We don't have any springs acting here, so we don't have any like restoring potential energy, spring potential energy. Okay, so K plus U is really going to be the kinetic energy plus the potential energy due to gravity. Okay, and that's going to be some constant value. So then if, for example, the ball up here at point A is at height h, okay, so let's say that it's at rest at that height h. Then what that tells us is that if we release the ball from rest, it will roll down the hill and it will roll along this track, but at each point along the track, it will have the same constant total mechanical energy that's equal to the mechanical energy of the ball at that initial position. Okay, so that means that if we have the ball is at rest at point A, then the initial mechanical energy of the entire system is going to be mgh plus K initial, which is going to be 0. So it's just going to be mgh. All right, and so then at any point along the track, the total mechanical energy will still be mgh. And so what that means is that the total mechanical energy is represented by this dashed black line on this curve here. Okay, and so then what we know is that the total mechanical energy is just equal to the sum of the kinetic plus the potential energies at each point along the track. And so then we can easily calculate the kinetic energy at any given point because we can read directly from the graph the potential energy. It's going to be the height of the track at each location, so mgh really at each location. And then the kinetic energy will just be the total energy is going to be mg times this initial height h minus whatever the potential energy is at a particular location. And so in other words, the kinetic energy is just given by the value of this green line here, the length of that green line, stretching from the horizontal line representing the total mechanical energy at all times, minus the potential energy at a given location. Okay, and so this can be really useful. It also tells us something about where the ball can go. Because remember, the total mechanical energy is going to be constant. Kinetic energy can't be negative. And so what that means is that the total energy can never go above this horizontal dashed line here. And so really then the potential energy can never go above that line, right? Because kinetic energy, it can't be negative. And so then the total energy is bound by this line here, this horizontal line. And so then I would know that over here at point D, this is where the ball would be coming to rest again, right? So it's at maximum potential energy, which means the kinetic energy would have to be equal to 0. And so this would be the point where the ball would momentarily come to rest, and then it would start sliding back down the track, going the opposite direction towards point C. Okay, and so we refer to that then as a turning point. So the ball will come up to point D, and then it will stop because it has maximum potential energy, no kinetic energy. It will turn around and slide back down. And so then as long as there's no friction in the track, the ball would just keep following that path back and forth, oscillating between points A and D. Okay, so that's it for the potential energy due to gravity, and now we want to look at the potential energy due to a spring. Okay, so to do this, let's imagine we have a horizontal spring that's initially stretched by an amount A from equilibrium. So in other words, X, that stretch amount is going to be equal to A. And then we're going to release that spring, or the block that's attached to the spring, we're going to release it from rest. Okay, and so then we have the situation that's drawn here. I have a spring, you can see its equilibrium position at X equals 0, and we've stretched it initially by some amount X equals A. Okay, and we're releasing this spring from rest. So what that means is that the total initial mechanical energy is going to be equal to total initial kinetic energy plus total initial potential energy. Here, because we have a spring that's on a horizontal surface, that means that the potential energy due to gravity is not going to change. We can pick the reference point for the potential energy due to gravity, or in other words, we can pick y equals 0 to be the height of the spring. And then we can just say that the gravitational potential energy here is always 0. Okay, and so what that means is that the kinetic plus potential energy in this initial state is just going to be 0 since our block is released from rest, so it has no kinetic energy, plus 1/2 kx squared, where x initially is equal to a. And so in other words, we get 1/2 ka squared. All right, and so that's our total initial kinetic and potential energies, or in other words, our total mechanical energy to start. All right, and then what we know is if there's no friction acting between the block and the sliding surface, then the total mechanical energy will be constant, right? So we have no non-conservative forces acting on our system. So the total mechanical energy at any time later will always be equal to this initial value, which is 1/2 ka squared. Since it's constant, it's not changing. All right, so at any point in time, as this spring is moving around, the total mechanical energy is always going to be 1/2 ka squared. And so what that means is that we can plot the total potential energy as a function of x position. All right, and when we do that, what we can do is we think about the fact that the total potential energy, which is shown by this red curve here, the potential energy due to the spring is 1/2 kx squared. And so when you plot that potential energy as a function of the position on the stretch from equilibrium, which is x, then you would get a parabola that's centered about the point x equals 0, which is where that potential energy is equal to 0. Okay, so you get this red curve here for the potential energy due to a spring as a function of x. All right, and then we just said that we're starting off with this initial potential energy because we've stretched our spring to the position x equals a. And so our initial potential energy is given by this point on the curve over here, which has a value of 1/2 ka squared. And now we know that since the total mechanical energy isn't changing at any moment in time, so for any position in the x direction, that the spring will have constant total mechanical energy equal to the value of the blue line. And so what that means is that's always going to be equal to the potential plus the kinetic energy. And so in other words, the kinetic energy is the amount that stretches from the blue line to the red curve, and the potential energy is the amount that stretches from the x-axis up to the red curve. Okay, and so then what we want to do is think about the maximum kinetic energy and the maximum potential energy here. So let's start with the maximum kinetic energy. When you have maximum kinetic energy, that means you have minimum potential energy, right? Because we know the total is always just equal to kinetic plus potential. So the point where we would have maximum kinetic energy would be the point where our potential energy is equal to 0. And so that's right at the equilibrium position of the spring. So right as the spring goes through its equilibrium position, it will have maximum kinetic energy. In other words, it's going to have maximum speed right there. And the value will just be exactly equal to the total mechanical energy, since we know that at that point U spring is going to be 0. So we're going to get maximum kinetic energy equal to 1/2 ka squared right at the point where our spring is going through the equilibrium position. Okay, so that's it for the maximum kinetic energy. Then at each point along the spring's path, it will have different values of the kinetic energy that are less than k max, down to the point where it's going to have k equal to 0, right? And so that's going to be right at the location x equals a. And then also you can see it will also happen over here at the location x equals minus a. At both of those 2 points, the potential energy is exactly equal to the total mechanical energy, which tells us that the kinetic energy must be 0 at those 2 points. Okay, and so this occurs either when the spring is stretched to some location a or compressed to some location minus a. All right, and then just like the toy car on the track, what that means is that's the maximum value that the potential energy can take. And so once that maximum potential energy is achieved, the spring, as it oscillates back and forth, it will have to turn around at each of these 2 points. So for example, if you start over here at x equals a, we release the spring. What's going to happen is the potential energy is going to be converted into kinetic energy. So you'll get to a point, the spring will be going through the equilibrium position at x equals 0. It'll have maximum kinetic energy. Then it's going to keep going. And so as it keeps going, it will reach this point eventually where it's compressed to some amount x equals minus a. And that's going to be where the potential energy due to the spring is equal to 1/2 ka squared, and kinetic energy is going to be 0. Then the potential energy, it can't keep growing, because for it to keep growing, it would have to go above that constant value, which it can't do. It's not allowed. So that ends up causing the spring to turn around, and then it'll start going back towards equilibrium. Okay, and so as it goes back towards equilibrium, then it'll get K max as it goes through equilibrium again, goes up, it'll stretch to some amount A, and then it turns around and it keeps oscillating back and forth. And so we refer then to these positions at the two ends, so at x equals minus A and x equals A, those are going to be our turning points in this case. All right. So let's do an example here. We have a toy car that's released from rest at a point halfway between points F and G. So over here somewhere. All right, and we want to know, ignoring friction, will the car reach each point on the track? And notice that there are two no options. So you'll have to pick both either yes or no, and then if you pick no, you're going to have to pick the appropriate explanation. Okay, so let's take a look here. So when I look at this track, I know that this point that the car was released from rest at, that's going to be equal to the maximum energy at all times as the car moves. Okay, so that's going to be the total mechanical energy all the time. And so what that tells me then is that the locations where the red curve, the potential energy curve, intersects with the total mechanical energy, that's going to be where the car turns around. Those are our turning points. And so then I can see that the car will not reach point A, and it also will not reach point G. Okay, so it's impossible. It'll slide back and forth between the 2 points where the blue curve reaches the red curve, but it'll never go above, so it'll never reach G or A. So I would say then that the answer is C here. All right, let's look at the same track, and now we want to know, ignoring friction, at which labeled point will the car have the greatest speed? Okay, so this one's really asking at which of the labeled points will the car have the maximum kinetic energy. So remember, the kinetic energy is the distance between the total mechanical energy and the potential energy, right? So the total mechanical energy minus the potential energy is going to be equal to the kinetic energy. All right, and so then the kinetic energy is greatest at the labeled point C here. That's where the potential energy is lowest, and so the kinetic energy is going to be highest. Of course, non-labeled points, I would pick this point over here. That's really the lowest potential energy, and that would give you the greatest kinetic energy. But since we're asked for the one that's labeled, I would have to go with point C here. Okay. All right, and so that kind of wraps up work done by conservative forces and conservation of energy, but what happens if we have both conservative and non-conservative forces acting on a system? Then we know that the total work done on the system is going to be equal to the work done by conservative forces, WC, plus the work done by non-conservative forces, WNC. All right, remember from the work kinetic energy theorem that the total work done by any type of force is equal to a change in kinetic energy. So W total is equal to delta K. All right, then remember that the work done by conservative forces, WC, causes a negative change in potential energy. So WC is equal to minus delta U. All right, so I've plugged that in here. And what we're left with then is delta K equals minus delta U plus WNC. So what I can do is I can just add delta U to both sides, and we get delta K plus delta U equals the work done by non-conservative forces. And then we remember that mechanical energy is kinetic plus potential energy, K plus U. And so the change in mechanical energy is just going to be the change in kinetic plus the change in potential energies. So that tells me that the left-hand side of this equation is really the change in mechanical energy of the system. All right, and so then what we're left with is that the change in mechanical energy of a system is equal to the work done by the non-conservative forces acting on the system. All right, and so then this is really useful for problem solving. We can rearrange this because the change in mechanical energy is really going to be the total final mechanical energy minus the total initial mechanical energy. And so that would be K final plus U final minus K initial plus U initial. So I could add that K initial and U initial over to the other side. And what we're left with is that K final plus U final, the total final kinetic plus potential energy, or in other words, the total mechanical energy at the final point, is equal to the total mechanical energy at the initial point plus the work done by non-conservative forces. All right, and so what that means is that if the final mechanical energy is less than the initial mechanical energy, the work done by non-conservative forces must be negative, right? So you would have kinetic energy plus potential energy minus something to give you a smaller number on the left-hand side. But if instead the final mechanical energy is greater than the initial, then we have some positive work done by non-conservative forces. In general, in here, we're going to be talking about work done by friction, for example. And so in most cases, we will be dealing with the case where the final mechanical energy is something less than the initial mechanical energy because we have negative work done by friction. The example where you have some sort of final kinetic plus potential energy that's greater than the initial mechanical energy, that's generally work done by heat. So in other words, heat flows into the system. All right, that's pretty much it. We're going to do some practice problems with work done by non-conservative forces. It can be very helpful in problem solving, just like that conservation of mechanical energy. Then you can avoid using some kinematic stuff and it makes your life a little bit easier. All right, so I just wanted to do a quick summary of work and energy so far. We're going to keep building on this, but this is a great foundation. So we just remember total work done is equal to change in kinetic energy. That was the work kinetic energy theorem. That total work is equal to conservative work plus non-conservative work. And we know that the work done by conservative forces is equal to minus the change in potential energy due to that particular conservative force. We defined mechanical energy as the sum of all kinetic plus potential energies. And so then if we have only conservative forces acting on a system, the mechanical energy is constant, the change in mechanical energy is 0, and so that means that the final mechanical energy must be equal to the total initial mechanical energy. If instead we have work done by non-conservative forces, then we know that the final mechanical energy is going to be equal to the initial plus whatever work is done by non-conservative forces. Often in here we'll be dealing with friction, and so that work done by a non-conservative force will be negative, and that will mean that our final kinetic energy is going to be less than our initial. Okay, and then we remember that K is always just 1/2 mv squared. Gravitational potential energy is mgy, and the spring potential energy is 1/2 kx squared. And of course, we have no potential energy due to friction. Friction does non-conservative work, and so it will be accounted for in that way. All right, and so now let's just go over a quick problem-solving technique when we have these conservation of energy problems, which includes the case where we have work done by non-conservative forces. That tells us that the work is being done to create different types of energy, just not mechanical energy, but the total energy is still conserved. Okay, so in all of these types of problems, you first want to start by drawing a free body diagram because it's really important to think about what forces are acting on your object, because that will tell you if you have, first of all, it'll tell you if you have only conservative forces acting, and then you know that mechanical energy will be constant. It will also then tell you if you have non-conservative forces acting, and then you have to think about the work done by non-conservative forces, right? So the mechanical energy between initial and final states will change due to the fact that you will also have this work done by non-conservative forces. All right, so it's important to draw a free body diagram to start out. All right, and so then once you've identified whether your forces are conservative or non-conservative, you can write down whether you're going to think that the total mechanical energy is constant or whether the change in mechanical energy will be equal to the work done by non-conservative forces. All right, so once you have that established, then you can write down the total initial mechanical energy. So the total initial mechanical energy is going to be equal to the total initial kinetic energy plus the total initial potential energy. And that potential energy, it could be gravitational, it could be due to a spring, or you could have both. And so you'll always want to think about adding those things together. All right, and then once you have the initial, you also want to write down the final. So I always draw like two states. What's happening in my initial state? What's happening in my final state? And then you want to write down what's my kinetic energy plus my potential energy, which again can include gravitational and spring potential energies in the final state. Then what you want to do is determine the work done by any non-conservative forces acting on your object. So remember, if there's no friction, if there's no non-conservative forces acting, then the work done by non-conservative forces will be 0. Otherwise, what you want to do is use the work equation. So work done by a non-conservative force is equal to that non-conservative force's magnitude, Fnc. So normally that's going to be the force of friction there. So the magnitude of that non-conservative force multiplied by the displacement of your object and the cosine of the angle between your non-conservative force acting on your object and the displacement of that object. So that will allow you to determine the non-conservative work done on your object. And then the last step is really just to put it all together and solve for your unknown. So the change in mechanical energy is equal to the work done by your non-conservative force. If there are no non-conservative forces, then the change in mechanical energy will be 0. But otherwise, you just want to use this work equation to relate the work done by a non-conservative force to the displacement of your object and also the magnitude of the force acting on that object. Okay, and so then from there, you should be able to solve for your unknown, and it should be much easier than going back to our old kinematics relationships. All right, so let's do a practice example here. We have a 50 kilogram skier going down a 78-meter high hill through a series of moguls. All right, so he starts from rest, so that's important. We're gonna start from rest at the top, and we're gonna slide to a stop at the bottom of the hill. So friction is the force responsible for stopping, and we want to know how much work does it do. All right, so this is a classic conservation of energy problem where we have work done by a non-conservative force. And so that tells me that the change in mechanical energy of the skier from the top of the hill to the bottom of the hill is going to be equal to the work done by a non-conservative force, which in this case is going to be friction. Or in other words, we could say that the change in kinetic energy plus the change in potential energy of the skier is equal to this work done by a non-conservative force. All right, and so this is a great example of why we want to use conservation of energy. If you were to actually think about calculating the friction between the skier and the hill, it would be impossible. As the skier is going over moguls and down a hill, his speed and his normal force are changing all the time. And so that means that to do this with kinematics, to actually calculate the force of friction at each moment in time, it would be nearly impossible. And so here, though, you're going to find that this is actually a very simple problem. All right, so let's go ahead and set it up. First of all, we can write out our knowns here. All right, so first thing we know, the skier is going down a 78-meter high hill. And so that tells me that y initial, his initial height, is at the top of the hill. It's going to be 78 meters. All right, and we know that he starts from rest, and so that tells me that v initial is going to be equal to 0 meters per second. All right, and then we slide to a stop at the bottom of the hill. So our initial condition is the top of the hill, the final condition is the bottom of the hill. He's sliding to a stop, so V final is going to be 0, and he's at the bottom of the hill, so if we let the bottom of the hill be a height of y equals 0, which was how we defined the initial height to be 78 meters, then Y final is just 0, and so is V final. Okay, and so then we know that we have these final and initial conditions. We don't have any springs, so we don't have to worry about spring potential energy. And so we can write down what is my initial total mechanical energy. It's going to be K initial plus U initial. Here that's going to be 1/2 mv initial squared plus mg y initial. We know that V initial is 0, and so his initial kinetic energy is 0, and so E initial is really just going to be mg times Y initial, which is that 78 meters. Okay, all right, and so that's E initial. Let's write down E final is equal to K final plus U final, which is going to be 1/2 mv final, which is 0, plus mgy final, which is also 0. So this is just going to be 0 plus 0, which is 0. All right, so we have our initial, we have our final, and then the work done by a non-conservative force, that's the thing we're solving for. So we actually don't need to think about the force or the displacement here, because really the entire thing, the work done by the non-conservative force, that's just what we're solving for. So all we have to do then is remember that delta E, the change in mechanical energy, which is equal to E final minus E initial, that is equal to the work done by a non-conservative force, and that's what we're looking for. Okay, so we are all ready to solve. E final is 0. E initial, remember, is mg times 78 meters. And that is equal to the work done by friction in this case. We know m and we know g, so this is going to be minus. Mass is 50 kilograms. G is 9.8 meters per second squared. Okay, and then we know we have 78 meters. Okay, and so when I calculated that out, I got negative 380 kilojoules. So it would be 380,000 joules. So I just converted it into kilojoules here. And that is going to be the work done by friction. And so that's it. So this super complicated kinematics problem where we'd have to think about forces and directions and all kinds of stuff. We'd have to think about centripetal force. Oh my gosh, it would be terrible. But so it's a super easy problem, right? So conservation of energy, it's a great principle and it's really useful in problem solving. So before you think kinematics, always think to yourself, can I solve this with conservation of energy? It will make your life so much easier. Okay. All right, so that's it for chapter 8. And up next, we're going to be moving on to chapter 9, which is collisions, momentum, and impulse. We'll be continuing to talk about energy, so we're going to keep building our muscle with using conservation of energy. But in addition, we're going to be talking about a quantity called momentum. All right, so I will see you in class.